Where did we come from? I mean, it's got to be the biggest question there is, right? But I'm not talking philosophically here. I'm talking chemically. How does a planet of rock and water and gas give rise to, well, to us? So let's do it. Let's open the case file on this 4-billion-year-old mystery.
You know, the great Carl Sagan put it so perfectly when he said, "We are star stuff, pondering the stars." And he was absolutely right. Every single atom in our bodies, except for maybe the hydrogen, was literally forged in the heart of a dying star. We are, in a very real sense, connected to the entire cosmos.
But that beautiful idea leaves us with a huge question. How does that star stuff start pondering? How do you get from simple, non-living chemicals to the incredibly complex, replicating, evolving system that we call life? That is the mystery we're cracking in this explainer.
We're going to approach this like the ultimate cold case. I mean, think about it. The scene of the crime is 4 billion years old. All the witnesses are long gone. And the clues? Well, they're buried deep in ancient rocks and even inside our own DNA.
Now, a really important point here. We're not looking for a single magical spark of life. That's not how science sees this. It's about a process, a whole series of small, believable chemical steps. It's about how simple parts, just by following the basic laws of physics, can gradually, piece by piece, build complexity.
Every good detective starts by reconstructing the crime scene. And for us, that means we need to get a clear picture of what the early Earth was actually like.
For decades, we had this image of the early Earth as a complete hellscape, a boiling ocean of magma. But it turns out the geological evidence has totally flipped that idea on its head. The reality seems to be a cool early Earth.
The clues that paint this new picture are these tiny, ancient zircon crystals. Some of them are 4.4 billion years old, and the specific type of oxygen locked inside them proves they could only form in liquid water. This is huge. It means oceans existed hundreds of millions of years earlier than we thought, giving life a much, much longer runway to get going.
So let's just put this on a timeline to really grasp the scale we're talking about. The Earth forms around 4.6 billion years ago, but by 4.4 billion years, we have evidence for oceans. This just blows the window for abiogenesis, the origin of life from non-life, wide open.
So the stage is set. But what about the ingredients? Well, the building blocks for life pretty much came from everywhere. From the air, you had lightning zapping volcanic plumes, creating amino acids. From the deep sea, you had hydrothermal vents using raw geochemical energy to make organic molecules. And of course, from space, a constant delivery of water and a rich soup of complex compounds via comets and asteroids.
Okay, so we've got the scene, and we've got the ingredients. Now for the central question. How did all these simple building blocks manage to assemble into something that was actually alive?
This leads us right into a classic biological paradox. You see, in all life today, DNA holds the instructions, right? But proteins do all the work, including building and copying that DNA. So, which one came first, the instructions or the machinery to read them? It feels like you can't have one without the other.
Well, the leading solution to this puzzle is the RNA world hypothesis. The idea is simple but brilliant. Before DNA and proteins, there was RNA. See, this simpler cousin of DNA is a real jack of all trades. It can store information like DNA, but it can also fold up and catalyze chemical reactions, a job that proteins mostly do now. So it could have been a one-molecule show, both the blueprint and the builder. Problem solved.
But what if life didn't start with a blueprint at all? The metabolism first idea suggests that before genes ever existed, there were just these self-sustaining chemical cycles. You can almost picture them as little chemical whirlpools or tiny engines, constantly powered by the energy from deep-sea vents. These reaction networks could grow and sustain themselves, and only later incorporate something like RNA. And there's a third crucial piece to this puzzle, the lipid world. Because, let's face it, a soup of chemicals floating around in a giant ocean isn't life. You need a container. This idea says the first, most important step was simple fats, lipids, naturally forming these tiny bubbles, or protocells. These bubbles would trap molecules inside, concentrating all the key ingredients and creating a little microreactor where the chemistry could really take off. So we've got these three potential paths, right? A genetics first path with the RNA world, an energy first path through metabolism, and a container first path with the lipid world. But you know what? They probably weren't competing ideas at all. The truth is likely that all of this was happening at once, working together to build the very first life.
Okay, that's all the theory, but what's the hard evidence? What are the actual smoking guns that make scientists think these ideas are on the right track?
We have to start with the famous Miller-Urey experiment from way back in 1953. This is the one where they zapped a mock early atmosphere and created amino acids. But the story got a massive update just recently.
So, in 2008, scientists found some of Miller's old, forgotten vials from a version of the experiment that simulated a volcanic plume. They analyzed them with modern tech, and the result was, wow, they found 22 different amino acids. That is a huge variety. It suggests that volcanic lightning could have been an incredibly powerful factory for pumping out life's building blocks.
Now what about those first cells, the containers? Well, Nobel laureate Jack Szostak showed how it could happen without any complex biology at all. It's amazing. Simple fatty acids just naturally form these little bubbles, these vesicles, in water. Then they soak up more fats from the water and get bigger. And when they get forced through a tiny gap, like pores in a rock, they physically split, creating daughter cells. It's growth and division, driven by nothing more than pure physics.
And the evidence from space? It is just undeniable. The Murchison meteorite, which fell back in 1969, was absolutely packed with over 70 different types of amino acids. And just recently, pristine samples brought back from the asteroid Bennu confirmed a rich supply of carbon and water. This tells us something profound. The raw materials for life aren't rare at all. They are everywhere in our solar system.
So let's pull all this together and really look at the big picture. Because understanding these mechanisms lets us completely reframe how we think about life's place in the universe.
You've probably heard this argument against abiogenesis, the junkyard tornado idea, that life forming by chance is like a tornado whipping through a junkyard and assembling a Boeing 747. But this totally misses the point. Science isn't proposing one single impossible leap. It's proposing a climb up what we call Mount Improbable, where lots of small, highly likely chemical steps build on each other one after the other.
And here's another myth you hear, that life, because it's so ordered, somehow violates the second law of thermodynamics, the rule that says disorder, or entropy, always increases. This is a complete misreading of the law. Earth isn't a closed box. Life creates its local order by taking in low-entropy energy from the sun and spitting out high-entropy heat. In fact, you could argue that life is the universe's most effective tool for creating disorder and obeying the second law.
So think about it. The building blocks are common. The process just seems to follow the fundamental laws of physics and chemistry. And that leads us to one final, profound question. If life is a natural, predictable result of a planet's chemistry, where else is it waiting? On icy moons like Enceladus and Europa, are we on the verge of solving not just our own 4 billion-year-old cold case, but one that's playing out right now across the cosmos?